Alright, so um, we're here today to take a look at something called Eigenfaces. It uses a technique um, called the principal components analysis that we covered on Friday, and that is a very fundamental algorithm for engineering and data analysis more generally. Um, so, what's the idea here? We're going to be taking a look at you have the script in front of you, hopefully, in the notes. And so we're going to be taking a look at these Matlab commands. Um, the Matlab script that we're looking at is eigenface example .m. And so first step, let's just go ahead and load in our data and see what we get. So if we type in load all faces 2, we'll see what the data is. I like to type in whos. So I'm actually using Matlab itself and not Octave, but the commands still work in Octave. So you see here we've got 2,410 faces or photos. Each photo is a vector. That's 32,256. Uh, the M and the N are giving you the sizes. So each photo is 192 by 160 or 168 by 192, I believe. Um, yeah, we'll see as we go along. If you get those mixed up, you're going to see a bunch of garbage in your image. We'll make an error so you can see what that looks like if you get those mixed up. Okay, and so we can go ahead and maybe we can go ahead and take a look at one. Image scale. Let's see. First, I'll just grab one at random. 363. Oop, I need to reshape that. I should turn off this suggested thing here. It's going to get in my way. Don't suggest anything to me. Gosh darn it. NM. Oh. You know, I think in your homework I reversed those. Sorry about that. We'll work it out. And I need the N and the N to be part of the reshape command. Okay. Good. So here's a sample photo. You can do a color map, gray. These are all in the notes there. Axis off and axis equal or square. Sometimes I use equal, sometimes I use square. Let's see. Where'd the photo go? There it is. Oops. Let's see if I can put it down here so I can find it again. Okay. There we go. Okay, so here's the photo. This is just a sample face. By the way, the faces are of different people. I think there's 38 people, and each person actually has multiple poses. And so the first person I think has 64 poses. So there's 62 columns. The first 62 columns of this data set correspond to one person, and then the next person has 62 poses. And so each pose has like different lighting. I think the first pose is like straight on without any, with like a uniform lighting, and then the other poses are with different kinds of lighting. And we'll see what the effect of that is when we take a look at the eigenfaces, or the eigenvectors of the covariance matrix. Okay, so what happens if I get the M and the N mixed up? Let's find out. So you get something like that. So if you see something like that in your figure, you know you got your width and your height mixed up. Okay, good. All right. Now, what's next? I think what we're going to do, instead of using the entire database for the building of our eigenvectors, because, you know, for the best basis, right, we're looking for the eigenvectors of the covariance matrix. We're going to use just the first 36 people. So there'll be 2 people left over, and there's a vector in here, n faces. If you look at that, this tells you how many poses each person has. There's 38 people, and most of them have 64, but there's a couple people that don't, like 63, 62, 63. Yeah, so that's what that's there for. Okay, so if I want the first, or the photos representing the first 36 people, right, I would sum the first 36 values here. And so if we do that, sum n faces 1 to 36. So we're going to use 2280, so our matrix is going to be 2282 columns long. Okay, good. All right. I see I'm running out of the bottom there. Let me blow that up a little bit so you can see it better. Okay, so now let's go ahead and say training faces. Again, this is in your script in the notes, and it's also available on the class website, so you don't have to. Let's see if I can type and talk at the same time. Training faces equals faces, all rows, and then columns 1, 2. I'll just say 2282 since I've already summed it. All right. So now I want the average face. So how do I do that? Average face is the mean of training faces. But remember, there's two different directions you can go. We want to go in the second direction, right? And we can double check ourselves. Let's check whose average face. Is that a vector? Yes. So average face we see here is 32256 by 1. So we know that that's an image. And so just to check that, let's go ahead and do image scale, average face. Oops, reshape. Average face. In this case, it's in an M. Good. And then we'll go ahead and do the axis off. Axis square, so it doesn't look too deformed. And there we go. Good. So this is the mean face of our 36 people. 36 isn't very many people, so that's why this face, if you get more people or a different data set, the mean looks very different. Okay, so in our homework problem, the mean face is going to be a lot different. Good. All right. So once we get the mean, what do we do with the mean? We mean subtract our data. So I'm going to call that XM just to be consistent. That'll be my training data, training faces, minus the average face. Okay. And whose? So XM, you'll notice, right, is 32256 by 2282, which is the correct size. Notice that I'm always typing whose because I think it's really important to keep track of the dimensions of your objects here, because this is a lot of linear algebra. If you can keep the dimensions right, you're in good shape. Good. That's all we have to do. Let's go ahead and take the SVD now. USV equals SVD XM. And we'll take 0 there. And now this is going to take a moment or two because these are kind of big. So how was your day today? It was pretty nice out there. I was supposed to go out and mow the lawn, but I didn't. I was sitting here coding in Python. Oh, you probably can't hear this, but my computer is starting to make some noises. It's starting to gear up. So we're doing this live. It won't take too much longer. Python takes about the same amount of time to do the SVD. There we go. Good. Let's type in whose. Good. And you can see that S is 2282 by 2282, which is kind of odd, right? Because S is really a diagonal matrix, so you really don't need all this stuff. Most of these numbers are zero, right? So really we just need to keep the diagonal, and in Python I think that is what comes out, is just the diagonal entries as a vector. So if you wanted to rewrite this as a matrix, you would have to use the diag command. Okay, the matrix U came out correctly, right? 32,256 by 2282. Remember, our basis is in 32,256 dimensional space, right? Those are where our basis vectors live. We have 2200 of them, or 2282 of them. Good. We haven't really talked about the matrix V very much. We will later on. Okay. First of all, let's take a look at these diagonal, or these entries in S. So if we take a look at those, go ahead and plot diag S. If you just plot the diagonal entries, you're not going to see it a lot. This is really a common thing. It starts off really big and then they drop off really fast. Okay, so that's indicative of something that might be a lower dimension. Um, but let's see if we can do a little bit better job of viewing that. So we'll take the log of the diagonal of S, and then we can kind of see it better. Good. And so you can see here that there's a value at which things take a dive. Let's see if I can use the Matlab thing there. There we go. 2269 it looks like. So that's an approximation. And in fact, should I do it? No. Well, what happens if I ask Matlab to do the rank of XM? What do you think it's going to do? Do you think it's going to be fast, or do you think it's going to be slow? Let's see. Uh-oh, it's slow. Do you know why it's so slow? It's because it's actually recomputing the SVD. So that's kind of weird, right? That, yeah. Anyway, um, so we'll see what it says. Oh, 2281. So it's actually telling us it's full rank, even though our picture says that you shouldn't have to count that much. So remember what we said about finding the values of this. If you square the singular values, what do you get? You get the eigenvalues. So evals of the covariance matrix, eigenvalues of the covariance matrix, not the SVD, is equal to the diagonal squared. And so if I take the eigenvalues and I guess, if we normalize the eigenvalues by taking, let's see, maybe SS equals evals divided by the sum of the evals. Remember that from the notes about the rank. Okay, so now this is not in the notes anymore. I'm kind of going off note, but this is one way to look to see if you take the cumulative sum of these values. Remember what we said? Whoops. Let me see. Let's just take the first 100 maybe. Oops. One to it. There we go. So you'll see what's happening here as you're adding more and more dimensions. Let's see if I can scroll up here. There's a long way. Oh, there we go. So the first eigenvector, or the first eigenvalue, has 36% of the overall variance. The first two has 71% of the variance. So how many eigenvalues do you need, or how many do you need? Yeah, how many do you need in order to get 90%? There's 90% right there. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. There's probably a better way to do that. 22 dimensions gives us 90% of the variance. Okay, and so the rest of this, right? This is going now from 22 to how many? 2,100 and whatever. 2,269. So you can see that this stuff is all filling in fine detail of the images. Okay, so again, this you could actually say it's almost 22 dimensions, but in order to get, we'll see what the reconstruction looks like with 22 dimensions. But okay, good. So that's one way of looking at the um, the normalized eigenvalues. You can also plot them. Oh, wasn't that the command I gave? I shouldn't go off notes. Oops, I didn't put that into an answer. Sorry about that. Let's just plot that. Plot. Oop. Plot the cumulative sum of SS1 to 100. Those are our, the cumulative sum of our eigen. So yeah, this is a nice plot, right? Because as the curve goes up, you can see what the percentage of the variance that we're capturing is. So you can see, for example, I'll just pick a point here, see if Matlab will give it to me. Yeah, 28 dimensions gives me 91% of the variance. 64 dimensions gives me 95% of the variance. How many do I need for 99%? I wonder. Am I up to 99? Oop, I need more for 99. Okay. Well, that makes sense. Okay, so I'm going to stop playing now and let's get back to work. So we've taken care of the analysis of our singular values, and now we want to take a look at the eigenfaces. So I'm going to copy and paste this, so you're not having to watch me type it. So these are in the notes again. Let's see, paste. Okay, I'm just, whoops. What did I do? Oh, I didn't get my F there. Let me try that one more time. Copy, paste. There we go. Okay, good. All right. So here's our eigenfaces. Looking pretty funky. So what you're looking at is a composition of lots of faces, right? And so the first one is the direction of most variance. Direction of most variance. And then the next one is orthogonal to the first one, right? And then the third one is orthogonal to the first two, and the fourth one is orthogonal to the first three. And so what we're seeing here is as you go down lower and lower, the highlights, or you're going to be working on different areas of the photo. So this first one is kind of the photo as one image, right? This the third one, I think, it looks very similar to the first, but it looks like you were kind of focusing on the nose in Eigenfaces 3 and 4. And what else is interesting about this is what happens if you plot the photographic negative of these. So let's go ahead and do that. Maybe I'll use a different figure for that. And then subplot 4j equals 1 to 4, subplot 2, 2, j, image scale, reshape negative u. Negative u is the photographic negative, by the way. That makes it easy. Color map and end. Good, so let's compare these. This was, oops, figure 1. Where's figure 3? Is here. So these are the photographic negatives of the photos we were just looking at. And I lost them. There they are. Figure 2. Let me put everything down below here so I can get back to it. Okay, I shouldn't be messing around like that, but okay, so there's our original eigenfaces. And these are their photographic negatives. So maybe I'll go that way. There we go. And so this is kind of interesting to see, especially the first one, right? The first eigenface to the photographic negative, because that first one, that's yeah, it's you can see that it's putting together the general shape of the face, and then I think in the photographic negative, in fact, in the second image, you can really see the difference, right? And in this one, if you're using the negative of the second eigenvector, you're working on the left side of the face, and if you're using the positive of that eigenvector, you're working on the right side of the face. And similarly, in eigenvector 3, if you've got the positive eigenvector, you're working on the highlights of the face, highlights of the nose. But if you've got the negative, what are you working on? Oh, you're working on eyebrows and the underneath the nose, and maybe a part of the jawline. Okay, and then this fourth one is just crazy. Okay, so that's fun to look at. So that's the photographic negative there. Okay, good. So those are the. So I would encourage you to take a look at those if you've got some time. They're fun to look at. Um, good. Now, step 6 is where we're at on the notes. So we're going to project. Oh, maybe I'll just bring in my code like this. Whoops. Gosh darn it. There we go. So step 6 is we're going to project the poses from persons 2 and 7 into the plane spanned by the basis vectors 5 and 6. And there's some formulas in here you don't have to worry about. Let's just go ahead and do that. You can look over the code. Person 1 is 2, person 2 is 7. Basis 1 is column 5, basis 2 is column 6. Those are 2 basis vectors. And so I've just written down how to compute those columns, and then my data is just the faces using those columns. And of course, don't forget to subtract off the average face, right? And then the coordinates. This is an important line right here. Do you remember how to compute the coordinates? This is the low dimensional line. Yeah, this is the low dimensional space here. That's line 43 is what we're looking at. This is 2-dimensional data, and so that's what we're actually going to be plotting. Okay, so in here I'll just say evaluate oh, I thought I could just evaluate the cell. I'll just do it this way. Evaluate selection. Oops. Let me get rid of figure 3 and redo that. Evaluate selection. There we go. Okay, so this is projecting the poses from person 2 and the poses from person 7 into the 2 basis vectors 5 and 6. So 5 is down below here and 6 is above. And you know what? I just realized that I think I might have messed up the next figure, so we'll have to see if we can fix that. Because if 5 is down here at the bottom, one of these vectors splits the data into 2, right? Is it 5 or 6? Eigenface 5 is down below here, and you see that both black and red dots, or black and red photos, are both kind of distributed across eigenvalue 5, or eigenvector 5. But in eigenvector 6, at 0, there's a line here that's separating the person 2 from person 7. And so it would be interesting to see, why is there this line here? So let's go in to the code and see if we can figure out why there's a line there between positive basis 6 and negative basis 6. And so let's see, this is going to be the optional subplot here. This is the faces data. 65 is the original number 7, and so this should have been 6 instead of 5. That's where I made the error, so you might change it in your notes, and we'll go ahead and run that now, and we'll see what this data looks like. Whoops. Oh well, let's go ahead and run it. Okay, and then run this code here real quick too, just to get that last one. Good. Here it is. Oh, now that's interesting. So what you're seeing here is the positive face and the negative face. Positive face and negative face in number 6. Do you see what's being grabbed here by the two? In this guy in the bottom, he's got a highlighted, uh, a real strong highlight on the brow and kind of darker eyes. And then the guy in the front, right, the eyes are more light and with a darker brow. And so that's what's splitting them apart, which is kind of bizarre. So again, the top eigenvector. So going back to that other plot again, maybe I'll call that figure 4 this time, so I don't overwrite what I just wrote here. Let's take a look at that again. Okay, so what's happening is that on the top, person 2 is corresponding to a positive value or a positive coordinate for basis vector 6, and the bottom person, which is person 7, has a negative value of eigenvector 6. And so you can kind of try to see why the two people are being split this way. It's kind of interesting when that happens, because these two eigenvectors off to the right are actually the same eigenvector. One's a positive and one's a negative of the same basis vector. So these are both basis vector number 6, and it's splitting persons 2 and 7. So that's kind of fun. And of course, the farther away you are, the difference. These are being arranged in such a way as when the illumination changes across the face. That's what's the variation is that you're seeing here. Okay, let's get back to those notes. This is kind of an interesting sidelight too. Good. All right, there's lots of interesting sidelights here. Now we're going to look at partial reconstruction of person 37 using these 4 different ranks. And so I like to use the subplot for that. So we'll go ahead and do that. Partial reconstructions mean what? This is the key line for that, right? Where you take U times U transpose times your data. That's projecting your data into these basis vectors. But of course, remember now that this is only going from 1 to either 50, or 1 to 150, or 1 to 500, or 1 to 1000. And so let's see what these reconstructions look like. Now these reconstructions are being taken for a person that was not in the original database, right? Person 37 was left out of the original database. So this is someone who was not in the original database. Do you think we have enough basis vectors to reconstruct their face? Oh, very interesting. So you'll have to trust me that this last photo down here is almost identical to the original image. You can see these last 2 photos are actually very close to the original image. Let's see, this is going from 500 dimensions to 1000 dimensions in this bottom row, and you can hardly see any change. You do see changes, and so that's how subtle some of these basis vectors are getting when you get into the high dimensions. And so that's why we might even cut this off, at 500 and say, oh, 500 eigenvectors is plenty. On the other hand, look at the rank 50 reconstruction. Rank 50 reconstruction was almost, you can't tell I don't think you can tell that was that person. When you get to 150, that's this upper right, it's starting to be recognizable, but it looks like the eyes don't really come into play or into shape until about 500. So it takes a lot of eigenvectors, I think, to get the eyes to be right. Good. Now the last one is kind of a fun example. We're going to take a look at the picture of a dog. And you might be saying, well, how would a picture of a dog be representative or represented by these eigenfaces that are from humans? Let's take a look. So do we have enough basis vectors to reconstruct the image of a dog. Well, let's take a look. This is pretty funky. Let me open that up a little bit. So this upper left is the original image. This middle one is, let me check what the dimension is. That is 50. So this is 50 and 100 dimensions. 50, or this is a rank 50 approximation to the dog. This is a rank 100 approximation to the dog. Let's see. Wow, that looks pretty weird. Okay, the lower left image is actually starting to look like the dog. How many did we need there? That's 600 eigenvector, or 600 vectors. Oh, no. Sorry about that. The top here is 50, 100, 400, 600. You can read that too. Okay, so the bottom row is 400, 600, and 1600. So that's 400, 600, and 1600. So by the time you get to 1600, oh, that's pretty darn close. And you know, that's the image of a dog. All right, so that was fun. Um, and So give this a try. This won't work in Octave Online. Um, Maybe I'll stop this and open up Octave Online just to show you what the homework data looks like there. And then, yeah, we'll talk later. How do I shut this off?